Hello, Sandeep sir.
Yes, sir.
Yeah, good evening, sir.
Yeah, please.
Sir, has everyone joined or
Sir, give me
is
a second. I
someone?
have someone maybe joined later. Not an issue. You may proceed, sir.
So,
Please.
okay, can I start?
Yeah, please, sir.
Okay, fine. Okay. Is my screen visible?
Yes, sir.
Okay, great. Okay. So, first of all, let me introduce you myself. I am Ajinkya Sadhve. I'm working as an assistant professor in Institute of Chemical Technology, Janna. Okay. And my specialization is in polymer engineering and technology. Okay. And currently I'm also pursuing PhD from ICT itself. And today I will be talking about polyurethanes and epoxides. So talking about polymers, I assume that you have gone through the basics of what exactly are the polymers, how the polymers are being synthesized, and what are the different polymers. Okay, so as a part of your this curriculum, you you might have gone through different polymers like polyolefins, polyvinyls. So same like it. Today we'll be talking about the polyurethanes. Okay, so basically, what is polyurethane? Just um, okay. So what is polyurethane? Polyurethane is nothing but a polymer which is composed of organic units. Okay. And those organic units, we call it as an urethane linkage. So urethane linkage is nothing but this highlighted square box which you see, which represents as NHCO linkage. So this NHCO linkage, we call it as an urethane linkage, and the polymers which are joined through this linkage, we call it as an polyurethane. So as you have learned, this is urethane linkage, one urethane linkage, and when it is being converted into n number of urethane linkages through different polymerization reactions, that polymer we call it as a polyurethane. Okay, so basically polyurethane is a material which defines the word versatile. Okay, so versatile, which we can see, it can mean anything. So, like many everyday items which you come across contains polyurethane in one or other form. Take an example of the shoes which you wear. So, the soles or the foam which is present in your shoes in the insole, we call it is a polyurethane. The mattresses which you use to sleep or on which you go to sleep uh, on a bed, it is nothing but a polyurethane. Okay. In car, you have the those seats. Those are nothing but the polyurethanes. Okay. So this polyurethane, it is a polymer which provides ample variety and customization opportunities. Okay, so why I'm talking about the ample opportunities and customization variety opportunities, because if you see, coming to the next slide, I will be talking about how it incorporates different aspects like flexibility, or how you can have a polyurethane foam which can be soft or which can be hard at the same time from the same material. So it is nothing but due to the structure property relationship of the molecules or the raw materials which are being used in the manufacturing of the polyurethanes. Okay, so if you see, polyurethanes, they are made by the reaction between alcohols. Alcohols means OH groups. Okay, so that alcohols can be two or more than two. So at least two alcohols should be there in the chemical reaction. And isocyanates. Okay, so isocyanates, again, it can be more than at least two or more than two. Okay, so it depends what are the molecules. So isocyanates means the molecules which has the NCO group in it, and alcohols means which have the OH group in it. So you have one molecule or one reactant which has OH group in it, and another reactant or raw material which has NCO group in it. So when these two groups react, we get this linkage, which we call it as an NHCO linkage or urethane linkage. Okay, so these PU are nothing but the carbonic acid derivatives. Okay, and again, this is the generalized scheme for polyurethane, which is being shown here, where this is the first raw material having NCO linkage and another raw material having OH linkage. And the reaction of both these molecules will give you NHCO linkage. Okay, so if you see, polyurethanes is the only class of polymers which can give you such n number of behaviors. Okay, like it can also exist in thermoplastic form. It can also exist in elastomeric form. It can also exist in thermoset form, in coatings, in adhesive forms. Okay, so you can also get the uh, materials which we call it as a composites. Okay, the simple sandwich structures can be obtained by using polyurethanes, and the properties of the polyurethanes, they range from to extremes, from like soft touch coatings to rock like hard rigid construction materials. Okay, so these mechanical chemical properties and whatever the ease of tailoring or the ease of leveraging the this raw materials, it produced a great interest in the industrial sector. Okay, and this enhancement, it can be done by manipulating only the raw materials, and along with it we can also add some different additives. So additives, I think you might not have gone recently. Uh, I think you have a coming lecture on additives. So surely we will talk about additives in the coming lectures. But to give you a short idea, a simple idea about what are additives. Additives are nothing but the materials which can be added to improve or to enhance the properties. Like, for example, to make the polyurethane material flame retardant. Okay, so to make the flame retardant, we generally add a flame retardant additives. Okay, so in that way, according to the application, these properties can be tailored. Okay, okay. So Now, talking about the versatility of polyurethanes. Now, polyurethanes, it has almost touched every area of materials engineering, like from shoes to aeronautical coatings, due to its multifaceted properties. Okay. And in the presence of chain extenders and also other additives, the building blocks of polyurethane, it can be trimmed down to two mother components basically, if it see, which we have already discussed, the polyol and isocyanate. Okay. And this polyol and isocyanate, these two molecules, they form different domains, or we can say different regions, okay, in the polyurethane. And these regions, they are responsible for this versatility of the polyurethane. Now, as you can see on the screen, you can see polyurethanes in automotives like seats, bumpers, doors, windows, airbags. Okay. Whereas in building and constructions, you can see in roofs, ceilings, walls. In medical, you can see hospital bedding, surgical drapes, wound dressings. Okay. Then in apparels, again you can see in sportswear, in appliances, you can see or you can find polyurethanes in refrigerators. You can also see polyurethanes in packaging applications for glasswares and medical devices, and also in some composite part. Okay, so like here you can see the PU can exist in foams, footwears, in paints as well. Okay, so this is the versatility which the polyurethane material exhibits, or the polyurethane material, it just shows you its presence from the, like as discussed, from the mattresses you sleep on till the aeronautical applications. Now, talking about the components of polyurethane formulation. Now, basically, I have talked about the two mother components. Okay, so two mother components means if you're using of isocyanate and polyol, obviously you will be getting a polyurethane. Okay, but to achieve or to make sure your polyurethane, it suffices its service life, or it serves its application properly, you need to add up some additives and add up some other components, okay, according to the required application. Now, when we so accordingly, we will talk about the different components which are generally being used for the formulation of the polyurethane. So first is obviously isocyanate. So this isocyanate is nothing but it is responsible for the reactivity of the polyurethane and the curing properties. Okay. So the examples of isocyanate containing molecules are toluene diisocyanate, methylene diphenyl diisocyanate, hexamethylene diisocyanate. Okay. We generally call abbreviate it as TDI, MDI, and HMDI. Then another component is polyols. So this polyol is another raw material or another molecule, okay, which reacts with isocyanate, okay, and including this polyol, it imparts or it helps in contributing the flexible long segments, which helps in producing elastic like materials. Okay, so polyols are nothing but molecules which have OH group at both the ends, and these between these OH groups they have an aliphatic or long chain. So this long chain or flexible chain, it imparts the flexibility and elasticity to the material. So examples of polyols are ethylene glycol, 1,4-butanediol, and 1,6-hexanediol. Okay, so apart from this, you can also use triols and other things. But basically, as we talked about mother components, we call it as a polyols. Okay. Then catalyst. Now, catalyst is, we can say it is the molecule or chemical which helps in speeding up the reaction. Okay, and that too at a lower temperatures. Now, what happens when you try to mix two different materials together? So after mixing the two different materials, the two different materials has to achieve an activation energy, or they needs to be activated for the reaction to get proceeded. Okay, and that activation energy is being achieved at a particular temperature. So certainly or mostly those temperatures are high, and even if we attain those temperatures, so there is a particular time period. Into that particular time period, your molecules will react. Okay, so to basically to lower down that time period and also to lower the temperatures, generally we use the catalyst. So catalyst, they just speed up the reaction, and also they reduce the temperature at which the reaction will be carried out. Okay, so examples of catalyst which we use in polyurethane are dibutyl tin dilaurate, which we call it as DBTDL. It is mostly or most commonly used or usually used catalyst, DBTDL. Then after that, we have dioctyl tin dilaurate. Okay. Then now these are the uh, basic things which are responsible for the polyurethane formation. Now after that, to impart the certain properties or to enhance the material's performance, we add some other components also. So, for example, talking about plasticizers. So, this plasticizer is nothing but a molecule which reduces the friction between the molecules of polyurethane. Okay, basically, what we can also say is this plasticizer, it reduces the material's hardness or it improves the material's flexibility. Okay, so example of plasticizer which can be used in polyurethane is either diethylene glycol benzoate or diethylene propylene glycol benzoate. And along with it, if you're planning to add or impart certain color to your polyurethane material, for example, you might have seen the polyurethane foams or the mattress foams which are available in different colors, like in some are available in black colors, some are available in pink colors. Okay, some are available in white colors. So depending upon the aesthetic requirement which the customer has, different pigments are being used. Okay, which impart the aesthetics to the material. Okay, so there are different pigments which are being incorporated to induce the color change. Then another component is cross linkers or chain extenders. Okay. Now, after incorporating some certain materials for polyurethane manufacturing, again, if you plan to improve the mechanical properties of the material or to make the structure more concrete, more rigid, then you can go for some structural modifications. So for structural modification, you can add a cross linkers or we can say chain extenders. So these chain extenders, what they do, they just extend the chains of the polyurethanes. So extending the chain, it can enhance the structure of the polyurethane, which enhances the tensile strength and hardness of your polyurethane. So again, in most of the cases, the diols can be used as in chain extenders, basically butanediol, ethylene glycol, triethanolamine, or glycol can also be used as in chain extenders. Okay, so now again, now if you try to make a foam out of it, or if you are planning to make a foam out of your polyurethane, now as I have previously mentioned, polyurethane, it can be soft to rigid one. Okay, so you can have a polyurethane foam, you can have a polyurethane in your shoe sole. Your shoe soles are also made of polyurethanes. Then you can have a rigid material of polyurethane in automotive applications. You can also have polyurethane in paints and coatings applications. Okay, so we'll discuss all those code applications into the coming slide. So now, if you plan to prepare a foam out of polyurethane, okay, now you need to add a blowing agent and surfactants into your polyurethane mixture, okay, while preparing the polyurethane. So blowing agents are nothing but the chemicals which helps in producing the PU foams, and it controls the foam cell structure. Okay, so how the this foam or cell structure is being created? Gases are being induced, which expands and it creates a foamy structure. Take an example of baking powder or baking soda. Sorry, baking soda in your this uh, cake preparation or dokla preparations. So as you can see, upon addition of baking soda, the dokla or the cake, it swells, okay, and it creates a foam cell, a cell-like structure. So same here it is being carried out. Generally, water is being used as one of the flowing agent, or cyclopentane is being used, hydrofluorocarbon is being used, or polydimethyl siloxane is being used. Okay. Then again, there are certain additives, as previously I have talked about. Additives are nothing but they just improve the stiffness and the tensile strength of your material. Along with it, they also reduce the cost. So such additives, they are generally fillers, which we call it as a fillers. So these fillers are being added in the polyurethanes. So examples are carbon fiber or carbon nanotube. Okay. Then another additive which or a component which I will talk about is the flame retardant. So as previously mentioned, flame retardant is the material or the molecule which has the tendency to inhibit or to resist the flame. So adding this flame retardant material in the polyurethane, it will reduce the flammability of the polyurethane, or we can say it will reduce the tendency of polyurethane to get ignited. So what kind of flame retardants can be incorporated? Triethyl phosphate or ammonium polyphosphate. So these are generally non-halogen based flame retardants. Previously, halogen based flame retardants were also being used. So halogen being based flame retardants means compounds which were having halogens like chlorine in it. Okay, chlorine, bromine. Okay, and now due to some environmental concerns, those halogen based flame retardants are being discarded, and now non-halogen flame retardants are being used. Okay. So any any doubt so far? Hello? Yes, students, just speak up. Any doubt so far?
No, sir, no doubt. Maybe I will ask after 15 minutes. I'm driving. Yeah.
Okay, okay, okay. Fine. okay. Now discussing the basic chemistry of polyurethane. Okay, now we have talked about the components of the polyurethane. Now again coming to the basic chemistry of polyurethane, and after that we will start with the applications of polyurethane. Okay, so unless we don't talk about the basic chemistry of polyurethane, you won't be able to understand how the same material or the single material can be used in different aspects of the applications. Okay, so talking about the basic chemistry of polyurethane, if you see the building blocks of the polyurethane, they are they can be separated, or they can be trimmed down into two segments. Okay, first is the polyol and another is isocyanate, right? So this polyol and this is isocyanate, and varying this polyol or the isocyanate, it can bring a drastic change in the properties of the polyurethane. Okay, as you can understand, if you need to prepare a flexible foam, so you need to change the content of polyol or isocyanate. And if you're trying to prepare a more rigid component, again varying the content of polyol or isocyanate can bring about this change. So this structure property relationship is very important in understanding and designing your polyurethane products. Okay, now this polyol and isocyanate, it forms a different domains. As you can see here, it is mentioned over the slides. And these different domains, they are responsible for imparting the properties like softness, flexibility, or hardness to your final product. Now, if you see these soft segments and hard segments are just illustrated here, a basic representation is given here. Okay. Now, as we have talked about the polyols, if you see from this structure, they have a longer chain length, which results in better mobility, and it improves the flexibility of the polyurethane. Okay, and diols, as you can use these diols of higher chain length. Just a second. As you can use these diols of higher chain length, so higher chain molecules will provide more flexibility. Now, if you talk about this isocyanate segment, this isocyanate, these are the hard segments. Okay, and these hard segments, they are also incorporated, or they are also, these hard segments is also contributed by the chain extenders also. Okay, so if you remember in the previous slide, we have talked about the chain extender. So chain extender and isocyanate, these both can incorporate or contribute to the hard segments of the polyurethane. And as the hard segments, they have tendency to pack very well. Okay, and due to this packing, or due to this packing arrangement, these molecules, they are very hard and non-flexible in nature. Okay, so due to this combination of hard and soft segments, this gives polyurethane its characteristics of being very highly versatile and effective for large range applications. So these imparts properties like softness, flexibility, or hardness to your final product. Okay. Now coming to the application part. Now, if you see the physical and chemical properties of polyurethane, they are highly dependent on polyol and isocyanate. So mostly 60 to 70% of properties of polyurethane is decided by the type of isocyanate and polyol which has been used. Okay. So, and these properties, these 60 to 70% properties can be altered either by changing the chain length of your raw material, the molecular weight of your raw material, the functionality of your raw material. Functionality, like as I've like simply putting up, functionality is nothing but how many OH groups or NCO groups are being present in your molecule. So as I have mentioned, you can have at least two OH groups. So if you increase the hydroxyl groups, again it will increase the properties, or it can. So this degree of customization, or this customization has given polyurethane an upper hand in various industrial applications. As you can see here in this slide, polyurethanes in foam applications. Okay, so if you talk about polyurethane foams, or you might have seen different foams in the market. So foams, they are either solvent based or water based. But nowadays, if you see, bio-based polyurethanes and other types are also available. And in general, solvent-based polyurethanes, they are produced from petroleum-based feedstocks. Okay, they are produced by petroleum-based feedstock. Okay, so and these are used widely due to their flexibility, abrasion resistance, and stability against water and certain chemicals. But the disposal of the solvent-based polyurethane, they creates a lot of environmental problems, like releasing some volatile or toxic organic compounds, and also they release a small amount of free isocyanate into the environment. Okay, so due to this reason, applications of water-based dispersion polyurethanes are also gaining popularity. Like waterborne polyurethane foams are being manufactured. Okay, so these foams, they can be prepared by dispersion a small amount of water. Okay, and these foams, they can give you the excellent characteristics. For example, having a low odor, resiliency, and lightweight. And these foams, they can provide excellent cushioning characteristics and can be easily molded to fit into the whatever the shape is being required, as you can see here in this picture. Okay, so these foams can be either flexible or rigid in nature. Okay, and the foams can be manufactured as the isocyanate component in the presence of the water, or when water is being added. As you might recall, during while talking about the different components of polyurethane, I've talked about the blowing agents and surfactants. So in blowing agents, one of the example was the water. Okay, so here water, in the presence of water, the water it helps NCO decompose into a carbonic acid, and as a result, CO2 is being generated, and this CO2, it acts as a blowing agent. Okay, and as a result, you get a foam. So these foams, they can be excellent in packaging due to their cushioning properties. Okay, wherever you are packing any fragile items, or you need to protect your products from the external damages, foams are being used. Okay, so there are other applications of foams also. We'll talk about in the coming slides. So one of the applications is like reticulated waterborne polyurethane filters. Okay, so as you can see, these are the filtration foams. Okay, and these filtration foams, which are made of waterborne polyurethane foams, they are called reticulated waterborne polyurethane filters. Okay, and these foams they are used in water. And again, foams, when you talk about foams are obviously lightweight and they have low odor and are highly resistant to mildews. And these foams can impart good chemical resistance, and due to their chemical resistance, they are widely used in the water filtration applications. Now, now, as they are used in filters, they are also used in air conditioners for the insulation applications. Okay, they can also be used in the as the sound absorbers in some acoustic chambers. In microphones, you might have seen reticulated foam is being present in face masks, in wiping pads. So there are a number of applications where these reticulated waterborne polyurethane foams are being playing a role. So these foams, generally, if you see the structure, they can be used for both air and liquid filtration also. And as per the application, they are available in different densities and they are available in different sizes also. Now, talking about the structure of the foam, if I say these foams have some cells which are uniform, okay, and these cells they obstruct the passage of the dust particles due to their high porosity and large surface area, okay, and due to this they are being used in the filtration applications. They are also used in the what we can say air cleaners, okay, or in air conditioners, automobiles, furnaces. In automobiles, like gaskets, sorry, this filtration assemblies. Okay, now use of polyurethane foams in construction applications. So talking about the construction applications, if you as day by day the climate change is rising and the energy costs are also being rising. So many countries they are increasing the regulations for saving energy and for making the different regulations concerned to the climate change. So they are urging, or the government is urging to many people for saving energy in buildings. So this step, it is just driving up the demand for better insulating materials, as we can say. So compared to insulating panels, which are made of polystyrene, like expanded polystyrene, we can say, or mineral wool or wood wool. So panels which are being made of rigid polyurethane or polyisocyanated foams, they display better insulating properties than any other insulating material, whatever is being available commercially today. Okay, so I'm comparing this in between the uh, this polystyrene or this mineral wool or wood wool. Okay, so these materials might not give better insulation properties as compared to the polyurethane material. So basically, this yes, sorry, yeah. So yeah, sorry, yeah, rigid PU foams, as you can see in this uh, image, it helps in saving energy, helps in resilience, okay, and it displays better insulating properties. So this results in lower space requirements, which is very much advantageous for the construction industries. And also, if we talk about the thermal conductivity of this rigid PU foam, it is determined depending upon its density, okay, or the selected blowing agent, and how porous the structure is, or the cell structure of your foam. So if you see here, there this is the house without the PU foam. This is the yellow shaded region is the PU foam. Now, now as it is not there, what happens due to, in mostly in summer seasons or in winter seasons, whatever the heat it flows from the exterior walls to the interior walls, it it affects the temperature, okay, of your uh, house or of your building. So when you insulate it with the PU foam, the inner temperature of your house or your building is being maintained in summer seasons as well as in winter seasons also. So like in summer seasons, your room or buildings it stays cool, whereas in winter seasons your building or your house it stays warm. Okay, so such is the advantage of the polyurethane material. So apart from this excellent insulating properties, we can say this PU it can also impart the fire performance, which is very much important in the construction industry. So like all organic materials, including wood and wool, as we have discussed before, polyurethane is also a flammable one. Okay, but if you add certain flame retardants, so this polyurethane foam it can be classified as having low or very normal flammability, and they can be used as thermal insulation in all kinds of building systems. Wherever this uh, materials or systems with low or very normal flammability are being required. Now, again, rigid PU forms in technical applications. So again, due to its good insulating properties, this material is of choice is good for the thermally insulating refrigerators, which provides higher energy efficiency. Now, if you see 95% of all the refrigerators which are being manufactured worldwide, they are all insulated with polyurethane. And the main thing or the main idea behind consuming this polyurethane is to consume the lower the energy consumption. Okay. So these refrigerators which are manufactured in a discontinuous process where the preformed outer shells, as you can see, this is the outer shell of the refrigerator. And this outer shell, it is being inserted into a support mold. Okay. Now, after inserting into the support mold, the reactive or liquid polyurethane component, they are injected into this cavity where they form up and fill the hollow spaces. As you can see in this image. Okay. So for better understanding, I have just included it here. This is the housing of the refrigerators, or we can say this is the uh, outer shell, okay, of the refrigerator. And in this outer shell, the liquid PU is being inserted, and it is being kept at a particular temperature. After keeping it particular temperature, within 10 seconds, this material is get filling up this space or void with the foam. Okay. So this foam, it provides good mechanical properties. good adhesion of the foam to the outer shells, which are used in the refrigeration industry, and it gives the possibility of filling up the complex spaces or the complex designs inside a housing with such rigid PU foam. So this is being again optimized using some PU formulations and manufacturing processes. Now the insulating performance also it depends upon the size, or we can say the cell size. As you can see here in the images, there are different cell sizes available, like which is for standard foam, then current state of the development. This is taken from one of the research paper. Okay. And then this is the nano foam. Okay. So depending upon this cell size, it can be said that smaller the diameter of the cell, the lower the thermal conductivity, and better it will give the insulating properties. Okay. And the conventional foams, they generally have a cell diameters which are greater than 180 mm. Okay. So if you continuously optimize the PU formulation, it can become possible to obtain the foams with very fine cell structures, like diameters less than 150 mm, and improved insulation performances. And that too, which can not affect your thermal conductivity and insulating properties also. Okay, so such nanoscale rigid foams with cell diameters of 150 nanometers can also be achieved. Now, if you see this kind of insulating material, it has the potential to reduce the energy consumption of the refrigerators. Okay. Now, finally, they are the rigid polyurethane foams. They are the standard for today's insulating materials. Okay. For example, in oil and gas pipelines, we can say, in chemical plants, we can say, in refrigerators, we can say, okay, which whatever the media is there or whatever the application is there, which requires the conveying of the cold or hot media. Okay. Now, what will happen? Insulating with this polyurethane rigid foam, it will help in minimizing the heat exchange between the whatever the medium is being conveyed and the surrounding environment. So it will efficiently minimize the heat exchange. And this performance has a direct and positive impact on the costing of your this overall system. Okay. Now talking about the, now this was what I was talking about the PU foaming in pipelines. So this is the steel pipe which is being surrounded with the polyurethane foams. Okay. And again it is being provided a covering with polyethylene sheet. So these pipes they are being used in oil and gas pipelines or some chemical plants, which conveys some cold and or hot media. Okay, and this can be if these pipes can efficiently or these materials can efficiently insulate over a temperature range from 196 degrees to plus 150 degrees Celsius. Okay, so such wide temperature range can be insulated, and this generally plays a major role in most of the hot water tanks, boilers, doors, window sections, and in numerous other applications. So just to give you an again a daily life example, hot water heaters, or we can say geysers, which are being installed in our bathrooms. Okay, so they are again being insulated with these rigid PU foams. Okay, so again, this is one of the technical insulation applications. Okay, Now, talking about the use of polyurethanes. Now, here I would not rather say polyurethane foams, but I would say polyurethanes. So, in this case, for footwear applications, you can also have polyurethanes in elastomeric form or polyurethanes in foam form. Okay. So, for footwear industries, if you see polyurethane foams, they are very much comfortable and affordable, and it helps in the long lasting of the quality. Okay. So generally, if you see the foot soles, they are made of polyurethane and they are lightweight. And if you see the shoes which you wear, they have excellent mechanical properties. If you twist and turn it, or if you subject it to a different kind of torsions, the material is very much, or material it stays very much together. Okay. So generally, these foams they are being used in trekking and sport shoes. And if we talk about the applications of polyurethane in footwears, it is increasing due to its long-lasting performances and cost effectiveness. So now mainly three types of polyurethane foams are there, like soft foam, rigid foam, and microcellular foams. And they are used in this footwear industries. And if you see from this
Sir,
image,
what you talk about footwear industry? What about
yes,
automotive seat industry? Which type of form you are using?
flexible foams are being used in the automotive industries. Okay. So
Seat design.
yes, seat design. In seat design, flexible foams are being used. Polyurethane.
Okay.
Yeah. So in this, as you can see from this picture, now this footwear it consists of different parts and components, like for example, upper and lining, uh, sole, insole, insock, and then adhesives. Okay, outsole. Okay, so if you see this insole, it is generally being placed i- above the inside sole. Okay, to provide cushioning to the foot and to absorb sweat while during the usage. And this insock is generally fixed in the footwear either permanently with adhesive or in a replaceable manner. And it is generally made up of either leather, fabric, or water-based polyurethane foam coated fabric. Okay, so it is a coated fabric, and this gives it the flexibility, compressibility, and the elastic properties to the sole. Okay, so mostly these, if you see the basic part or the uh, outsoles and the insoles are the most important parts where the PU is being used. Okay, now as we have talked about the polyurethanes in different aspects and majorly in foam applications. Now we will just move towards the somewhat different material or different aspect of the polyurethane, which is the paints and coatings. So as we have talked about, it can polyurethane foams can also be used or foams can also be manufactured. Polyurethane can also be used in paints and coatings applications. Okay. So if you see the overall paints and coating system or polyurethane coating system, there are two types of system, which is reactive one and non-reactive one. So in reactive, you have two types again, oven curing polyurethanes and moisture cured polyurethanes. Okay. So in oven curing polyurethanes, they are just similar to the two component systems. Okay. In which they accept the block isocyanate is used to provide a stable one pack mix with the polyol or isocyanate or polyamide. And then isocyanate is then deblocked when stirred and hence reacts. Okay, so basically this includes powder coats which consume 10% of all urethane in paints. When you talk about moisture cured PUs, these are one component system which are high molecular weight and low free isocyanate containing prepolymers. And these polymers they cure by reacting with moisture from the air, which forms the urea linkages. And this constitutes or this represents 5% of all urethane in paints. Okay. And when we talk about non-reactive, so non-reactive it comprises of the uh, thermoplastic urethane-based lacquers or aqueous PU dispersions, or you can say urethane oils or alkates. And these systems have in common that isocyanates do not react during application. Okay. And so if you see the binders or polyurethane binders, on account of these diverse formulations and variable properties, they are the preferred choice when it comes to formulating high quality coatings. Now, why PU paints? Okay. Why only polyurethane paints or mostly polyurethane paints? So if you see, as we have talked about polyurethane, it imparts UV resistance. It again imparts chemical resistance and versatile chemistry. Okay, so versatile chemistry, I mean, again, you can just change the different components and you can again change the chemistry of the material. Okay, so today, whatever the top coats are being used, okay, so basically in automotive coatings or in whatever the coatings are there, generally there are different systems like 2 layer, 3 layer, 4 layer, multi-layer coats. So basically you have a base coat, then you have a top coat, then you have uh, other coats, or you have a base coat, then primer, then top coat. Likewise, so whatever the top coats are used today, roughly 30% of top coats are made up of polyurethanes. Okay, and these coatings or these polyurethanes they are being generally applied using water-borne system or solvent-borne system, or mostly in powder coating systems also. Okay, now talking about polyurethane adhesives. Now you might wonder polyurethanes are being present in foam applications also. The foams can be flexible also, rigid also. So these foams are being present in your car seats, okay, or in your shoe soles also. In your automotives or in your car, along with your car seats, where you have polyurethane foams, you also have a polyurethane which is being spread over the car surface as a top coat. Okay, so along with it, you can also find polyurethane serving as an adhesives also. Okay, so due to their high performance and a wide range of demands, these adhesives can be essentially whole range of isocyanates and polyols, okay, which are accessible to different industries. So these adhesives, they are supplied in solvents as waterborne dispersions in 100% systems and high molecular weight films. And if you see, these adhesives can be used in footwears, in flexible packagings, in constructions, or in transportations. So in transportations, where you have instrumentation panel, or you have door streams, or ceiling of a headline, or headliners in automotives. In that section, you can see polyurethane serving as an adhesives. Okay, so that was all about the polyurethane materials. Okay.
Sir, one question. In generally automotive seats, by changing the hardness, we are changing the comfort. So
Yes.
how is the process we are doing this in manufacturing?
Okay. So in manufacturing now, see what happens. as I have talked about, now let me go to the previous slides where it will be easy to explain. Okay, yeah. So now, as we have talked about, there are two different building
Actually,
blocks.
my basic question was maybe I'm reiterating that generally to increase the comfort, we are playing with the density and hardness. That is also one of the contributor factor. So how we are achieving in terms of chemical composition or maybe manufacturing point of view? I need input from you. Yeah. Thank you, sir.
Yes, yes. From the manufacturing point of view, as I have said, so basically, if you want to manufacture a flexible component, you need a isocyanate to polyol ratio. Okay, we basically call it as an NCO index. Okay, so basically, if you see, this index is generally 1 is to 0.8. Okay, like 1 will be isocyanate, 0.8 will be polyol. So now, as I have mentioned, polyol it contributes to the flexible segment. Isocyanate it contributes to the hard segment. So now, if you are planning to increase the hardness,
Where is the isocyanate? I can't able to see.
this is the isocyanate.
This is mentioned 4 MDI it is showing.
Yes, yes. It is 4,4-MDI. So isocyanate, what I've told you in the previous slide, isocyanate is molecules which has NCO linkages in it. Okay.
Okay.
And polyol is molecule which has OH linkage in it. Okay.
Okay.
So 4,4-MDI is nothing but methyl diisocyanate.
Okay.
Okay. So this is one of the example of isocyanate which I have mentioned here. There are other isocyanate also like toluene diisocyanate, okay, or hexamethylene diisocyanate, okay. So its structure differs. So if you see, this contributes to the hard segment. This contributes, polyol contributes to the soft segment. So if you increase the concentration or composition of the isocyanate, and if you reduce the composition of the polyol, you will get a harder segments more. More harder segments means you will have a hard components or rigid components of polyurethane. But if you are planning to make your polyurethane more flexible, so you can go for reducing the isocyanate segments and increasing the flexible segments or soft segments, we can say. So in this way, you can just change the ratio, and by changing the ratio you can just go on the achieving the desired properties of a material.
This you talk about sore hardness, right?
Yes, this we talk about for hardness, or we can say for the flexibility, we can also say for soft to the hard segment.
But sore hardness, maybe we can say.
For sure hardness you can also say.
And what about density? How we are playing with density? Because there's also variable density in same mold can be achieved.
Yes, now talking about the density. So now density, now I'm just considering the density part in case of foams. Okay. So
Okay.
now in case of foams, when you produce a certain or when you use a certain type of blowing agent, so the amount of gas which will be evolved during the foam production, it helps in imparting the density to your material. Okay, so this how it will impart the density based upon the cellular structure or the formation of this cellular structure. See, this is the cellular structure. How this cell size, how how well is this cellular structure? Depending upon this cellular structure, the density it also gets affected.
So how this cellular structure creating?
So this cellular structure is being created due to the blowing agent, which is being mixed while preparing the polyurethane. So again, you need to adjust the ratio of isocyanate and polyurethane, sorry, isocyanate and polyol, and along with it, you need to control the foaming, okay, or we can say the gas generation. How you are dispersing the blowing agent in your polyurethane matrix. So if you disperse it suddenly,
Basically, this cell is creating due to the blowing agent, that chemical reaction, right?
so now let's say for example, you are adding water as a blowing agent. So if you add water uh, in one shot, okay, or in a single in at a single time, so you will have a different density of the foam, different cell structure. And whereas if you add slowly or slow addition of water is being done in polyurethane, so you will get a different cell structure. Okay. So in and also depending upon the temperature, what temperature you are adding. So if it is very much higher temperature, again your cell size it will be uncontrollable, and it will affect the density. And if you have the temperature within an optimum range, again you will be able to control the cell size and cellular structure of your foam. Got it?
Yeah, but let's suppose if it is a block of a that PU form, or maybe we can say seed. So at particular one corner I need this density, at particular one corner I need less density. Is it possible?
No, it is not possible that you can achieve a variable density at one corner or another corner. As you can see, this foam generation, it is a uh, it is a single one-time process. Okay, so this generation or foam generation is taking place simultaneously in all the areas. So you do not have the leverage of altering the density in one part and another part.
Maybe two input for PU form, different density we can pour.
To achieve a PU foam of different density, you need to manufacture a PU foam differently then.
Different
Or you need to employ, yeah, you need to employ different systems in it.
yeah, by adding two, let's suppose two input, two nozzle, like that maybe.
Yes, yes. In that way you can do, but you will encounter a very much phase separation in it.
Sorry.
You might encounter a phase separation if you are doing a if you're trying to insert the PU solution from two different ends or two different PU solutions, and if you're trying to achieve different densities at different regions, so you might get a phase separated regions.
Yeah.
Okay, so phase separated regions means, like, take an example of oil and water. Okay,
Got
so
it.
as the oil and water can be space separated, likewise these different regions can be separated, and again it will affect your these properties of the final PU form.
Okay. Yeah, got it.
Okay, okay. So
Is there any agent which is blowing it or blowing agent separately? Is it marked in the this thing equation?
which is not in this
The previous
list.
you have shown on equation that there you told polyalloy and this some say cyanide you told, but where is that agent you told? No, blowing agent. Whether it is
Blowing agent.
ah,
Blowing agent, see, I have also given you the examples of the blowing agent, what blowing agents are being used. Here you can see water, cyclopentane, hydrofluorocarbon, polydimethyl siloxanes. These are some of the examples of the blowing agents. Apart from this, there are also another blowing agents which are being used, but they are not used in this polyurethane systems. Okay, because because those blowing agents they are used in different systems. Like, say for example, now you need to prepare a polyethylene foam, okay, or cross-linked polyethylene foam, which will serve in water tank applications. So for that system, you have different types of foam. For example, azodicarbonamide. It is again one type of blowing agent. Okay, but you cannot use that azodicarbonamide in this type of materials.
it's for a blow mold, no?
Sorry,
The water tank is made out of a blow molding.
Yes, it is made up of blow molding also and rotational molding also. So again, depending upon blow molding,
Okay.
yeah.
Okay. Your voice in between it got broken, sir.
Okay. Am I audible now properly?
Yeah, yes.
Yeah. So
Maybe
I was telling,
internet is disconnecting, maybe kind of what we are feeling, maybe. But right now, okay.
okay, okay. So I think there might be some this uh, network stability issues, I think.
Okay, sir. Epox.
Okay. Yeah. So what I was telling, even if the water tanks can be manufactured using blow molding also and rotational molding also. So again, depending upon which process is being used, your material it also differs. So in blow molding, mostly HDP based materials are being used. So and in rotational molding, NLDP materials are being used for the manufacturing of water tanks.
Okay,
And
sir.
again, yeah, again, depending upon the processing techniques, there are different properties which are being imparted into the material. So that is the different aspect which is not within the scope of our lecture.
Okay.
Yeah. Okay. So shall we continue with the epoxides now?
Yeah, yes, sir.
Yeah. Okay. Thank you. Now again, talking about epoxides or epoxy resin, we can say polyepoxides, epoxy, or epoxy resins. They are nothing but they represent a special class of highly reactive polymers or prepolymers which contain this epoxide group. Okay, this is the epoxide group, or we can say the oxygen ring. Okay, so the molecules which contain this ring in their group or in their structure, we call it as an epoxy molecules. So this term epoxy, okay, it represents any basic or cured end products of epoxy resins. And these epoxy resins can undergo catalytic homopolymerization with themselves, which can form a cross-link structure, or we can say a 3D network, or they can react with different reactants, such as aliphatics or aromatic amines, some acid derivatives, amides, esters. Okay, so there are n number of reactants. Now, these co-reactants, they are commonly called as curatives or hardeners, and the cross-linking reaction is often called to as a curing. Okay, now let me talk about this structure. Now, before talking about it, let me give you the basic example of what actually epoxy or epoxides are. Have you heard about the MSIL?
Yeah, in plumbing kind of MCL we heard about.
Yes, so you might have seen that if you have if you have ever bought MSIL it contains two different components, okay, or two different materials are being given to you, and when you mix those two different materials, while mixing, you need to rub those materials, and after mixing, when you apply it, after some time, it gets stick to that whatever part you are applying it, or whatever part you are selling it. Okay, so those two materials are nothing but one of them is epoxy resin, and another one is hardener, or we can say curing agent. Okay, so when this epoxy is mixed with the curing agent, so due to the application of rubbing or mixing, it generates heat, a reaction is induced, and due to this induced reaction, a cross-link network is being formed, and due to which, after a certain period of time, your part or that M seal, it gets cured or it becomes hard or rigid. Have you experienced it?
Yes, sir.
Yeah,
So yeah, that is the most common example I can give you about the epoxy resins. So if you see, epoxies
I
again
think
has
I think the hardener case in that hand layup process FRP in that
yes,
liquid.
yes, yes,
Yeah,
yes, that I have also
is it
included.
same material?
Yes, yes, it is the same material. Hardener is the again the same material which, yes, you have mentioned about the hand layer process. I have also included that part in the applications of the epoxies. Again, epoxies can be used to manufacture composite materials using hand layer technique. So during that
You
hand
mean
layer,
to say hardener is same both cases? What about resin? Resin is different or same? Resin
uh,
material.
materials are same, but we can say the chemistry of the materials is different. So as I've mentioned, there can be uh, for a polyol, as I'm just explaining the different a generalized term, polyol. So polyol it can be butanediol, hexanediol, polyethylene glycol. So these are the different names. So likewise, hardener in hardener, amine based hardeners can be different is a general name. So in case of amine based hardener, there are different kinds of molecules which has amine group in it. Okay, so again, depending upon the system, molecules can be different or chemicals can be different. But the basic chemistry for it is the same. Got it?
Got it. Yeah.
Yeah. So again, as compared to the polyurethane, again, epoxy is again one of the versatile classes of the thermoset material, which again can serve with a different range of applications. And these materials can be tailored through the use of different pre-polymers or different raw materials. And if you see the overall market or the commercial market of the epoxy, 70% of epoxy resins, they are mostly of diglycidyl ether of bisphenol A, or we can say DEEBA. So this is the structure or general structure of the diglycidyl ether of bisphenol A. And this is the mostly 70% of all epoxy which is being used in the commercial applications. Now, if you see the role of this epoxy resins in different components, this is the epoxide ring or oxygen ring. And this ring, it is very much highly strained or constrained, and due to which it is very much reactive to the different chemical species. So this serves as a cross-linking site or curing site. This is the only site where the curing can occur. Okay, when you mix the hardener or curing agent, so it reacts with this site and curing takes place. So along with this, you have these two different rings. So these rings, again, they are very much poor in UV stability. So UV stability means if you use the epoxy resin in exterior applications where it will be exposed to the sunlight. So in such cases, your epoxy resin will degrade very quickly due to the poor UV stability. And this poor UV stability is due to the presence of these two phenol rings, or we can say these benzene rings. Then if you see, epoxies are also used in adhesive applications, and they provide excellent adhesion to various substrates. And this adhesion, it comes due to the presence of this hydroxyl groups or this molecule. So it imparts the adhesion properties to the epoxy material. Again, talking about these rings, though they provide the poor UV stability, they increase the thermal and chemical resistance of the epoxy system. So this is the non-epoxy part, and non-epoxy part, it can be aliphatic, cycloaliphatic, or aromatic. Okay, and in order to produce a cross-link structure or 3D network, or in order to cure your epoxy resin, there needs to be a functionality of two, at least two. As we have seen in case of polyurethane also, here also you need a functionality of two. Functionality of two means you need two epoxy resins. This is the one, this is the second. So such two epoxy resins should be present here, and these two epoxy resins can react with the curing agent to form a cross-link network. So see, these are the different epoxy resin types. You can see first, as I have mentioned, 70% of epoxy is diglycidyl ether of bisphenol A. Then rest of the 30% comprises of the trimethyl propane or tetrafunctional epoxy resin or cycloaliphatic epoxy or novolac epoxy resin. Okay. Now, this is how the different types of epoxy resins are being present. And these co-reactants, as I mentioned, they are commonly called as curatives or hardeners. And the cross-linking reaction or the hardening reaction, it is commonly called as a curing. Okay. And generally, this curing of epoxides, it makes them brittle in nature due to the high degree of cross-linking or due to the high cross-linking. And this curing, it also results in formation of the thermosetting nature of this polymer with high mechanical strength and good thermal and chemical stability, as it can be imparted through these rings. So again, these can be modified for precise applications by proper selection of resins, cross-linking agents, and modifiers. Okay, so these epoxy resins, they have a broad range of applications like surface coatings, uh, like electrical insulations, fiber reinforced plastic materials, okay, or paint brushes, electrical components, or in adhesives. Now, talking about the characteristics of the epoxy resins, they exhibit a wide range of characteristics, which includes having a wide range of varieties because of proper selection of different resins, modifying and curing agents. So, wide range of epoxy resins, which ranges from low viscosity liquids to high melting point solids, it can be designed. Okay. So these are the characteristics. I'm talking about characteristics of epoxy resin, how they are advantages. So second characteristics is like talking about wide range of curings. Okay. So these wide range of curing can be achieved by proper selection of the curing agents. And these can be cured at a wide temperature range of 0 degrees Celsius to 180 degrees Celsius. Now, as I have given you previously the example of MSIL. MSIL, it gets cured at room temperature just through the application of rubbing or shearing. As you are mixing the two different materials, so you are just creating a heat with the help of rubbing, or we can say shearing, and due to which your epoxy is getting cured. Then third is the strong adhesion due to the very high surface functionalities, such as previously discussed, the hydroxyl group and the ether bonds. So these possess a strong adhesion ability with different substrates, especially metallic surfaces also. Then the fourth characteristics is low shrinkage with unlike most thermosetting polymers, epoxy-based polymers, they are mostly associated with low shrinkage. And their shrinkage is so low that when cured, epoxy resins, they have a shrinkage rate less than 2%. Then you have mechanical properties. So the cured epoxy resins, which are either cured themselves or by using hardeners, they possess excellent mechanical strength, which makes them suitable for different reagents for several industrial applications. Another characteristics is like the excellent electrical properties. So the cured resins, it acts as excellent insulators, which have good arc resistant and surface leakage resistant materials over a wide range of temperature during its application. Okay, means even if you have epoxy resins, so it has good arc and surface resistance. That means from its surface, current leakage is negligible, or we can say it is very much low. So therefore, it is being used as an excellent electrical insulator. Then again, seventh characteristic is cured epoxy resins. They acquire excellent chemical stability for acidic as well as basic environments. And this chemical stability, it is attributed due to the highest cross-linking or highest curing, which avoids the penetration of chemical molecules within the structure. Then talking about the dimensional stabilities, now these epoxies possess good durability and dimensional stabilities, as it can be correlated with the low shrinkage of the epoxy resins. Then ninth is they have good microbial resistance, especially against fungal attack. So apart from the above mentioned one, okay, they possess excellent corrosion resistance and high tensile strength. Now talking about the curing stages of epoxy resins. Now curing is nothing but the chemical process in which the epoxies, they are allowed to react with suitable curative reagent. Okay. And after reacting, they form a cross-linked network, which is very much essential for high mechanical, chemical, and heat resistance behavior. So this process, we call it as a curing. Now, this, if you see, this is the cross-cured object. Okay. This is the curing agent, and this is the base liquid agent. When heat is being applied, these bonds, they get cross-linked, and after cross-linking, they form this such kind of 3D network. Okay, or we can say cross-linked network. So this curing, or we can say gelation also, it is exothermic process. Exothermic means heat is being produced. Okay. कभी देखना, okay. Just observe whenever you try to mix MCl, okay, while mixing, you might experience the generation of heat on the mixing surface. If you try to mix it on the palm, your palm will become hot, okay, due to the action of mixing. Why? Because it is an exothermic process. It generates heat. Okay, and in some circumstances, it also causes the thermal emulation of the three-dimensional cross-link networks. Okay, so this gelation, it can be accomplished either by reacting with itself, okay, or with some other curing agent. So as we have mentioned that the epoxy ring is very much highly strained and reactive, and it readily undergoes ring opening reaction. So the ring it opens, and the active hydrogen of the curing agent reacts with the epoxy. So if you see here, I have mentioned the reactivity trend of the different or some common hardeners towards the epoxy. So thiol, which has SH linkage of SH group, they are very much highly reactive towards the epoxies. Then aliphatic amines. So aliphatic amines means amines which has NH group. Cycloaliphatic NH groups which has cyclic ring present in it. Then aromatic amine again which has benzene ring like structure present in it. Then acid anhydride, and last phenol. So phenol is very much least reactive towards this curing process. Okay, and this reaction of these alcohols, thiols, and amines with epoxies, they form the epoxy resins. Okay, so these are the general. This is a curing reaction of the different curing process of the epoxies, and as mentioned, due to the exothermic, this exothermic curing, it also requires the temperatures up to 200 degrees Celsius also. Okay, so there are different curing stages as you can see from this picture. So epoxy, it goes through three different stages during the curing process, which starts the instant when you mix the epoxy hardener and epoxy resin together. So first, what happens during the first stage? So when you mix the epoxy, the first stage, it is called as an open time. Okay, so during this stage, the epoxy is in a liquid stage, and this stage, the hardener and resin are mixed to start the reaction. So during this stage, the mixture, it will remain in liquid form, and it is workable. Okay, means you can change the shape or whatever changes needs to be done, it can be done during this first stage. Okay, and whatever the clamping and whatever the assembly or packing of the mold is done, it should be done during this stage. Okay, so then there is the another stage, second stage. So during the second stage, your epoxy, now it is not workable anymore. Okay, instead its consistency will quickly change from being tacky to firm, like hard rubber one. Okay, now for example, if you try to press your thumbnail or your finger into the epoxy, you can see a dent in the material during this stage. Okay, and the final stage of the curing for epoxy is the process where the epoxy becomes a solid, a completely dry and hard, rigid material. So during this stage, you will not be able to make any dent using your thumbnail or your finger. Okay. So now coming to the paints or the application part. Now again, talking about epoxy, why epoxy paints? Again, there are several advantages or several features which epoxy exhibits, like low shrinkage, corrosion resistance, and excellent adhesion. So due to which, again, epoxy are used in different paints and coatings applications. For example, like heavy duty anti-corrosion applications. So these applications are due to their exceptional properties such as easy processing, high safety, then excellent solvent and chemical resistance, and excellent adhesion to many substrates. Now, if you see in the industries, you might have seen such kind of coatings, right? So these coatings are nothing but the epoxy floor coatings. So epoxy can also be used in floor coatings. So the point why the epoxies are used in floor coatings are due to the excellent adhesion, excellent toughness, okay, excellent mechanical properties and abrasion properties. So as there are heavy machineries or heavy equipments in the industries, so due to the uh, because there is a requirement of high wear and tear, sorry, due to the very much high wear and tear, your floor might get deteriorated in the industry. So to sustain that floor, epoxy resins are being coated onto the floor. Okay. And again, inside the metal cans and containers, they are often coated with epoxy resins. So due to the corrosion resistance. So especially when acidic foods are being packed, so to avoid corrosion inside the metal cans, it is being coated through epoxies. Then talking about epoxy adhesives, again, epoxy adhesives, it plays a major part called structural adhesives. So these high performance adhesives, they are used in the construction of aircraft, automobiles, bicycles, boats, golf clubs, snowboards. Okay. And here I have again mentioned one example of araldite. Again, araldite is one of the commercial example. Then this is the composite fuselage. This is the part which is being used in aircraft. So here also epoxy adhesives are being used to bond the composite fuselage. Okay. Then talking about epoxy composites. So again, epoxy plays a critical role in composite manufacturing. Okay, especially when epoxies are being combined with the reinforced materials. So they can serve as an excellent composites material, and they are the thermoset plastics. These resins, they
Sir, your voice has gone. We could not hear you, sir. We could not hear you, sir. Hello. Sir, your voice is gone.
hello.
Yeah, now
Am I
you're.
audible now? Okay, okay. Yeah, sorry for the interruption. Yeah. So so epoxy resins, as it can be changed to the sorry, it can be used as a composites. As you can see, composites is the mixture of different materials, which the material which has low weight to high strength ratio. Okay, and these materials, they provide a strength, durability, and resistance to the overall material. Now, when you use epoxy resins in case of composites for impregnation and lamination also, heat resistance, mechanical strength, and flame retardancy are the primary properties which are being demanded. And if you use the epoxy resins in FRP moldings, so in case of FRPs, the fast curing is being demanded. So you can also see there are adhesives, epoxy adhesives, which are also being used in soundproofing composites, as epoxies, they exhibit the sound absorbing properties or good insulating properties. So they are also being used in this adhesive as an adhesive in soundproofing composites. Okay, so that was all about epoxy and polyurethanes. So to sum up, we have done with today the polyurethanes and epoxies. We have seen how the different chemistry and the different raw materials of both the materials can give us a leverage to change or to enhance, modify the properties of the final material, and the different applications of both the materials, the wide range of applications where these materials can be used. Okay, so any doubts so far?
Uh, no doubt, sir.
Yes.
No,
Uh,
no, sir.
Okay, then can we stop here today for today?
yes, sir. Tomorrow, which are the topic we are going to cover?
Uh, Tomorrow's schedule, I am not clear about the tomorrow's schedule because now I will be meeting you on 4th November.
Sir,
So for
at the glance, just can you show the first few slides, sir?
first few slides.
For 1 to 10 slides. Just
Okay.
okay. Here it is only urethane linker. Polyol,
Yes.
polyol will be another one, na?
Yes. See, this is the linkage which is being generated after reacting isocyanate and polyol.
Okay, this is after isocyanate and polyol. Okay.
Yes.
Next slide, sir. Isocyanate and polyol. So here R represents that continuous chain.
Yes. R represents the continuous chain.
Then what about R1? That is also
R1, yes, that is also a continuous chain that can be also aliphatic or aromatic. So again, this is for polyol, this is for isocyanate. So that's why it is given as R and R1.
okay. Okay. NCO, what is the full form of NCO, sir?
And so it is the linkage. Okay, in molecule, it is the linkage.
Okay, it's a separate
Ha,
nitrogen, oxygen, huh?
ha, nitrogen, carbon, and oxygen. Linkage of nitrogen, carbon, and oxygen.
Okay, okay, sir. Next, it's just usage. Okay, sir. Next, sir. Next slide. Okay, sir. From here, you have already shown. Thank you, sir.
Next slide, or shall we stop?
In that only one thing. I asked about that. No. In the next slide. Next slide.
Ha,
Here you we are that gas blowing agent we are telling, no, that gas blowing agent cannot be a part of the equation, no, it will be separator. It is part is only to generate, or it is also in the equation.
In this equation, we do not have the blowing agent. Okay, so this is the basic polyurethane reaction. Okay, now if you want to make a polyurethane foam, okay, as depicted here, so in this case, you need to add blowing agent
Okay.
like water.
Okay.
Only if you want to make a foam.
Okay. So that is the agent we are inducing into that reaction. So that
Yes,
kept
that
us.
is one type of additive, we can say.
Okay. And it is also part of the equation and the output also.
Yes. So it is the part of equation in which case when
Second.
you want to generate a polyurethane foam.
Okay. Next slide, sir. That is a polyurethane foam, no? Next
Yes,
slide.
this is not polyurethane foam. Now here
That-
you can see this man is spraying the polyurethane and it is getting converted into the foam. It is getting foamed.
Okay, 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 okay. Okay. Sir, here this H2O where we can see in the after reaction phase, NCO is there, CO2 is there, H2, NH2, it become NH2. There already
Yes,
one H is there and one H we are adding from this thing, water. How it is got split?
see,
Where is it?
see
Where is the gas?
what happens? What happens here? It is just for to simplify the reaction or to make us understand the reaction. Here only NCO is being shown.
Okay.
Okay. Along with it, alcohol is also there.
Ah,
Polyol is also there. Okay. So along with these agents, H2O is added. Water is being added. So when water is being added, what happens? Exothermic reaction takes place, which makes the
okay.
decomposition of this NCO in this carbamic acid. This is the carbamic acid. Now this carbamic acid it gets decomposed into this NH2 and CO2. Okay.
Okay.
Huh. You can
NH2 and
see,
that is okay.
yes,
Yeah.
it gets decomposed into NH2 and CO2. And this CO2, it acts as a blowing agent or gas. It generates a gas. Now CO2 is a gas, right?
Okay.
So due to this gas, the formation of the cellular structure takes place or the material expands, we can say in simple language.
Okay. Okay. Understood. Understood, sir.
Okay. So this is the next slide.
Okay, sir.
This is the next slide.
Okay. Thank you, sir.
Okay. So any more doubts?
No, sir. Thank you.
So Sandeep sir, can we stop here then?
Yes, sir.
Okay, fine. It was nice to meet you all. Nice interacting with you. We'll meet on 4th November then.
Okay, sir. Thank you, sir.
Okay.
Thank you.
Thank you all.
Happy
Yeah.
Diwali. Happy Diwali to all.
Yes, happy Diwali to all.
Sir, from tomorrow is a holiday, sir.
I'm not sure about this your schedule. I think Sandeep
Sir,
sir will
as per
confirm
schedule
you.
is tomorrow and after tomorrow is morning, sir.
Okay, if you are already being circulated with a schedule, so you can, I think, stick to that schedule. But you can just confirm with this Sandeep sir.
Yeah, yes, sir. Sure. Thank you.
Okay, thank you. Signing off.
Yes, sir.
Hello, Sandeep, sir. Hello.